Welcome to today's lesson on arithmetic series. We've been talking about geometric and arithmetic sequences, but now we're going to talk about a series. The only thing the difference between a sequence and a series is just a list of numbers or shapes or whatever, but we've been working with strictly numbers, where a series is the expression for the sum of all the terms of that sequence. So you see here I got a couple examples where I have the 6, 9, 12, 15, 18, where I just have them listed with commas between them. That's just a sequence. If we take and basically what we're doing is replacing those commas with plus signs, we're turning that into a series. And once we've turned it into a series with these plus signs, we can evaluate those. We can add all those terms up and find out the total value of that series. Here we have another example. Just listing them as 3, 7, 11, 15 is a sequence, but writing them as 3 plus 7 plus 11 plus 15 plus ... That is actually what a series is. We also want to talk about the terms finite and infinite. Finite, there's a set number of terms in the either series or sequence, and series in this case here. So you can see that we have 1, 2, 3, 4, and it goes ... Normally when you see ... you think that it goes on forever and ever. But by putting this 10 here, they're saying, hey, we're going to go from 4, and all this ... fills up all the spaces with that pattern up until you get to 10. So that still is finite. So finite could have a ... in the middle of it, or it can just list all the terms there together. When we talk about infinite, it's an unlimited number of terms, where we have 1, 2, 3, 4, ... and we don't have an end to it. It goes on forever and ever. That's infinite. I briefly said the word about evaluating or finding the sum of those. We can find the sum or evaluate any finite series. If it's infinite, it goes on forever. Once you think you've added up all the terms, there's still a next term to add to it. And then there's a next one. That's what infinity means. It goes on forever. But if we have a set number of terms, we can use this formula right here. And I know there's a lot of little gadgets here, but let's go through these things. This S just simply stands for sum. The N, that's how many terms we're going to add up. It's more of a notation here. In the formula, this N again stands for how many numbers there are. So we do have to know how many numbers there are. And then it's always divided by 2. And then in parentheses, we have this A1 plus AN. A1 always represents the first term. A1 is the first term of that series. AN is the last term of that series. You say, well, why isn't there a number? Because each series has a different number of terms. I don't want to put A10 in here, and then all of a sudden we're dealing with a series that has 12, 15, 20 terms in it. So this N just represents, hey, it's the last one. You don't know until you get to that particular problem what that number is actually going to be, whether it's A10 or A12, A15, whatever it is. We'll continue on here. And I've asked the question, find the sum of each series. So we have this series that's 5, 13, 21, ... 61. Again, this ... that doesn't mean it goes on forever. It means it fills in all the spots in between. But we know there's 8 terms. It's giving this information to us. Well, if we go back to our formula real quick, what are the pieces of information that we need? We need to know N, the number of terms. We can find that. The first term and the last term. Well, if we go back to this one here, do we have the number of terms? Yeah, 8. So I'm going to put S8, and I'm going to put an 8 above that 2. Remember, this is always a 2 here. Then in parentheses, the first term of the series. I get that from right there. That's the first term of the series. AN is the last term. Well, the last term is 61. And then I just use my order of operations, and I simplify this expression. I do what's inside the parentheses first. 5 plus 61 is 66. I can do this division right here. 8 divided by 2 is 4. So now I have 4 times 66 to get us a total of 264. So the sum of this series right here, if I evaluate this series, comes to a total of 264. We come down to another example. 2, 4, 6, dot, dot, dot. It goes to 28, but they're telling us there's 14 terms. So again, what are the pieces we need? We need the number of terms, we need the first term, and we need the last term. So I can fill those in. So S 14, so I'm finding the sum of 14 terms, equals that same 14 over 2. Then in parentheses, A1 is 2, it's the first term, plus AN is the last term, it's 28. And if I simplify that, I can do this division out here because it doesn't that division doesn't affect what's inside here. So I get 7. Inside here, 2 plus 28 is 30. And then when I multiply 7 times 30, I get a total of 210. So if I evaluate this series of 14 terms that has the pattern of 2, 4, 6, dot, dot, dot up to 28, I get a total sum of 214. We'll look at one last example here for this part. I got a first term of 0, a 0.4, a 0.8, a 1.2, and then dot, dot, dot. So I'm filling in these numbers here up to 3.2. We could, with this dot, 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 we could figure out the pattern. I could write all these terms out up until I get to 3.2, and then I could go back and add those. That's fine. It's perfectly acceptable as long as we have a reasonable number of terms. It's telling us we only have 9 terms, so that wouldn't be too bad. If this was like 25 terms or 30 terms or 50 terms, I don't think we want to write out 50 terms and then go back and try to add all those 50 terms when all we need is 3 pieces of information from this series, and we can use this formula to find the sum. So we're going to find the sum of 9 terms, so S9 equals 9 over 2 times our first term in parentheses is 0, plus our last term is 3.2. So when I start to simplify this, 9 over 2 is 4.5. 0 plus 3.2 is 3.2. And when I multiply those, I get a final sum of 14.4. So if I evaluate the series that goes from 0, 0.4, 0.8, 1.2, dot, 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 up to 3.2, knowing there's 9 terms, I get a final sum of 14.4 there. This says write the related series for each finite sequence, then evaluate each series. Remember, evaluate means to add them up. So here I have this sequence of 21, 18, 15, 12, 9, 6, and 3. That's a sequence because it's just a list of numbers. I want to write it into a series, so I'm not changing any one of these numbers. I'm not adding any new numbers. I'm just, like I said before, basically replacing the commas with plus signs. So I change it to 21 plus 18 plus 15 plus 12 plus 9 plus 6 plus 3. That is the series. And when I add those all up, because they're all right there already, it doesn't really make a lot of sense to use the formula, although we could. We could just add those terms up. And when we evaluate this sequence, after we've turned it into a series, we get a total of 84. Again, we have another example here. We have 100, 99, 98, dot, 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 down to 93. That's a sequence. We want to write the series for that. And so we start with the 100 plus 99 plus 98. It's not that far from 98 to 93, so I think we'll go ahead and write these. 97, 96, 95, 94, all the way down to 93. If we were to have used the formula to add these up here in a second, I would have had to have known how many pieces are in between there. It's not just this series is not just 1, 2, 3, 4 pieces. We can clearly see there's more in there. So since it's so close together, we would have had to have counted out those terms anyways, it's not a bad idea to write those. And then again, we're trying to evaluate this. So we want to add all those up. And when we do, we get a grand total of 772. So if we evaluate the sequence of 100, 99, 98 down to 93, we've turned that into a series, which is the sum of all of those numbers, and it adds up to 772. One last example here. It goes 1, negative 3, dot, dot, dot. So it fills in all these, and into negative 13. Well, I want to take that sequence and I want to turn it into a series still again. So again, I'm changing these into pluses. Commas get replaced with pluses. This looks like it's a pattern decreasing by 2. So then I want to add negative 5, and I want to add negative 7, add negative 9, add negative 11, and then we finally get to that negative 13. So we have this now as a series. We want to find the sum. So we take all these numbers, 1, and when we're adding a negative, we're really subtracting. So this is 1, minus 3, minus 5, on down the list. When we add those all together, or subtract them basically, we end up with negative 48 as our final evaluation of that sequence that we turned into a series. The last thing we want to talk about in this lesson are the following series finite or infinite. We talked about that at the start of the lesson. Remember, finite means there's a set number of terms. I can actually go in and I can count them. I could have 1,000,000 terms, but if I have 1,000,000 terms, I know I can count those. But if I have something that goes on forever, I can never count all those terms. So if we look at this first series here, it says 1 plus 2 plus 3 plus 4 plus dot, dot, dot. Well, we said just because we see a dot, 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 that doesn't automatically make it infinite. If it has an ending point, then it would make it finite. In this case, it does not have an ending point. So because this dot, dot, dot is at the end, it is infinite. It does not have a stopping point. Now, if we look at this one where it says 1 plus 2 plus 3 plus 4, which is the same start to the one above it, I have a dot, 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 but now I've put an ending number there. I know that I'm only going up to 25. That stops it. It sets a limit to that. So there is a finite number of terms. I can actually count those. That makes that series finite. And then the last one, that's 10 plus 20 plus 30 plus 40 plus 50. There's no dot, dot, dot. This is it. I can see all the terms. I can count that there are 1, 2, 3, 4, 5 terms. If I can see all the terms, if I can count them all, then that is finite as well. And that concludes our first lesson with arithmetic series.